Okay, so today we'll be discussing about one of the interesting algorithm in machine learning called k-nearest neighbor. Okay, so or we call it KNN as well. So it's a supervised classification algorithm mainly used for our classification purpose. Okay, so mainly it is used for classification. If I CATION classification, but it can be used for regression as well. Okay, but mainly people use it only for classification. Now before we go deeper into this particular algorithm, okay, so let us see logically how it works. Okay, so then we get a fair idea about what kind of scenario we can use and how to use it. Okay, now for that what I'll do is I'll just show you a data, let's say our data distribution. Okay, so I'll just draw a graph over here. Okay, now let's say we have couple of red points here. Okay, one red point is over here, one red point is over here, and one red point is over here, and we have couple of blue points, let's say, okay, here, 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 and here. Suppose I want to know the class of this particular star data point. So if I just say these red points and blue points are representing my training data set, okay, we'll see an example of training data set as well, and this is our test data set. I want to know the class of it. So if you remember from my previous video, in classifications problem, what we do generally, we basically determine the class of that problem, right? That means if I just give you an example of, let's say, based on certain data set, let's say age and how much loan they have taken, okay, for a particular person, if I have a data set, and if based on that data, if I just wanted to determine whether they will default or not, okay, while repaying that loan. So it's a classification problem, right? Because at the end of the day, we are determining whether that particular person will be going with default or not, yes or no problem. And that means the output of this particular problems are different classes, right? So that means for the test data, we just need to determine which class it belongs to, correct? So for KNN, what we generally do is we basically determine the k nearest points. Okay, so if I just say k nearest point, okay, k can take any value, okay, from 1 to infinite. We'll see when it's going to infinite what's going to happen. Okay, now generally in normal scenarios, most of the case value we generally set from 3 to 10. Okay, now if I just, let's say k equals to, if I just take 3, that means for this particular star point, we are going to find 3 nearest point over here. Okay, and if we just draw a circle over there, so let us do that one. So if I just say logically, these 3 are if you see the picture wise, if you see just the way I have drawn it over here, it looks like these 3 red points are nearest to this particular star, right? We'll see how to determine the nearest point. And if I just draw a circle over here, okay, a boundary basically, so, and then we'll take vote from these 3 nearest point. Okay, now if you see it over here, for this star, this yellow star, all these 3 nearest points are red, right? So that means we have 3 red nearest, 3 red points, and we have 0 blue points, right? Now that means we can confidently say this particular guy, this particular star, the class of this particular star is going to be red. Okay, so this is how logically this particular algorithm works. Now if you see it over here, if you remember from previous algorithms we discussed for classifications and regressions, right? We talked about logistic regression, we talked about linear regression as well for predicting problem. All of these actually have certain kind of pre-assumption about the data, right? So that's why we call those algorithms as parametric algorithm. Okay, parametric algorithm. Now KNN do not do any kind of assumption about the underlying data, so that's why KNN is generally called non-parametric algorithm. Okay, non-parametric in nature. Now let us take an example about a real world example. The example just now I have given about the age and the loan they have taken, whether the default or not. Now for that we have a data set. Okay, so this is the data set for age, the loan they have taken in terms of the loan amount will be in, okay, let me pull it out over here. I think, okay, so if I just pull inside it over here, so we have age in terms of year, okay, we have loan in terms of dollar, and whether they have default it or not. Okay, so if we just copy this data set over there, okay, we'll just copy this data set for there, copy, and we'll go it over here, we'll paste it. Okay, so this is our data set, right? Now if we just draw a graph from this data, if we just plot it over here in a XY plane, okay, so let's say in x-axis I'll be in 10, I'll just go down a little bit, so it will be 10, 10, 20, 30, 40, 50, 60, let's say 70, because in x-axis we will be plotting our age. Okay, so if we are giving age as x-axis, okay, now in the y-axis if I just plot the loan over here, okay, so let's say 50,000, 50k, we have 100k because it is in terms of k only, we have 150k, we have 200k, we have 250k. Okay, I think there is no amount which is greater than 250k over here, right? So if I just plot it over here, so age, the first plot will be age 25, it's nearly 40,000. so if I just give the default which is no as red point and default which is yes as blue point, so first one is no, right? So loan amount is nearly 40k. So if I just give something over here, okay, second one 35 is 60k. So for this one it will be nearly over here, right? Now okay, it will be little bit down over here because 35 will be mostly here. Now for 45 it is 80k, so that means I'll be almost touching more than this one. Now for 20, right, age 20, it will be 200k to 20k, right? So that means here all are in only till now, right? Now for 35 it is 120k, but this is also in, right? So that means nearly over here. Now again for 52 it is 18k, so that means for 52 it will be somehow nearly here. So all my red points are done, and if I just plot the blue points now, so 23 it will be 95k, so that means almost over here, right? Now 40 it will be 62k, so that means 40 it will be nearly about here, right? So 35 we have 60k, that means somehow over here, Now for 60 it will be 100k, that means here. For 40 it will be 28 to 20k, that means somehow over here. It will be a little bit down, right? Now for 33 it is 150k, that means it is almost over here. So this is our data distribution over there, right? Now we want to determine a input variable, let's say input data called 48. That means a person with age of 48, okay, he has taken the loan of 142k, okay. So our job is to determine whether he will be default or not, okay. So that's the algorithm output will be. So if I just plot 42 over 48 over here and 142k, so 48 will be, sorry about that. So this is our yellow point, right? So that means 142k will be somewhere around here, correct? So now by using KNN we are going to determine what is the neighbor, right? So for that let us assume first, we'll see that later how to vary k. Let us assume first k equals to 3, right? So that means we need to determine the 3 nearest neighbor of this particular yellow point, right? And among those neighbors, which one is basically the more default value? That means if I say in among those 3 neighbors I get 2n and 1y, so that means I will tell with more confidence that this yellow will be member of n. That means this is not going to default. If I get 2y or 3y at least, okay, 3y, then I'll be telling who is going to default, okay. So that is the way this particular algorithm works. So now to make this thing shorter, what I have done is in this particular Excel sheet, okay, so I have computed the distances. Now it's time to talk about distances. Now in KNN we can have lot of different kinds of distances, okay. So one is Euclidean distance. So if I just write it down over here, EUCLIDEAN, Euclidean distance, okay. So I think if you this is the most simplistic distance formula you have. So this is just in Cartesian coordinate. So if I just little bit go up, so it is just normal a distance formula between 2 points, right? If I just know the coordinates of this problem, and we know the coordinates of this problem because of these things, because of our input data, right? So that means it's generally depicted as square root of, okay, for each and every point, okay. So that means over here we want to determine the distance from this yellow points to all other points, right? Then we will take the most 3 nearest points, right? So that means x1 minus, that means if I just say xi minus yi, so xi minus yi is the x value, that means x value of this yellow points, that means 48, minus x value of any of this point, plus Control Z, because it will not be plus. So that means for each and every feature, so if I talk about age and loan as a feature, that means our x-axis and y-axis. So each and every feature from the point you want to calculate the distance to other point, right? Suppose this guy over here. So if I just draw a line over here, that means if I say for each and every point from this yellow point, I'm going to compute this distance, right? So this guy and I have to sum them out for all. For that means for each and every feature I want to give this minus from the point of x point, from the same feature the point I want to calculate the distance. Okay, then I equals to 1 to n for all the different features. Okay, so this is the Euclidean distance. So there are another distance. Now other distance could be Manhattan. I'll just go down a bit. Okay, so Manhattan distance. So this formula is similar to this Euclidean distance only, but instead of taking the okay, here I have done one mistake, so it will be a square. Okay, so for each and every feature we will just minus their corresponding values and taking the square and sum it up. Okay, so Manhattan distance we take summation. Okay, just if I just write it something like this, summation I equals to 1 to number of features, then the absolute value of it. Okay, this is the Manhattan distance. There is another distance called Minkowski distance, WSKI, Minkowski distance. I may be creating a separate video to just go deeper into this how this distances formula came up. Okay, I'll be creating a separate video for that. Now here also it will be similar. I equals to 1 to n. Let me write it carefully. Equals to 1 to n. So absolute value of xi minus yi, then to the power q, and this whole stuff to the power 1 by q. Okay, so we mainly use this Euclidean distance, and which we will be using it in this particular problem itself. Now if you see, like this Euclidean and Manhattan distance is one of the case for this Minkowski distance, but Minkowski distance is actually generalizing these two guys over here. Okay, maybe I'll be creating separate video for them if we need to go very deeper into this one. But let us try to go by this Euclidean distance and compute that one. Okay, now for that what I have done is in this Excel sheet. Okay, so I have already computed the distance from this guy to all other data points over here using the same formula. If you see it over here, what I have done for each feature, I have given 48 minus 25, that means A14 minus A2, then square it up, then plus for feature number B, that means loan, 142k minus 40k, that is what B14 minus B2 I have done, then square it up, then the whole stuff I have given the square root. Similarly for other data point also I have done the same thing over here. Okay, so this is all the points I got, distances I got. That means if I just tally with this particular figure over here, that means we are basically computed this line values over here, right, for each and every point from the point we wanted to classify. Now what I have done is over here is I have sorted them out from lowest to highest point. Okay, because we need to identify the three nearest point from the point of 48, this 142k, right? And if we just sort it out, so there are 3 points, 800, 22,000 and 42,000. That means this guy, 8,000, that means this guy over here. So that means 33, 150k. So if I just point it out over here, so we have, okay, let me put it in this color. So we have this guy over here. This is this is the most nearest point over here, right? So this is 8,000, right? Now the second point is 22k. So that means this guy, 35, 120k. So if I just point it over here, so 35, 120, because this is our second nearest point, correct? Now our third nearest point is, if we just go by 42,000, that means this guy over here, 60, 100k. So if I just tally it over here, 60, 100k. So these 3 points are our nearest point, right? And if I just see it over here, this guy is y, this guy is y, and this guy is n over here, right? So that means we can say this guy will be y, because there are more y's compared to the number of n, right? So that means for k equals to 3, our KNN algorithm is saying for a guy with this loan amount and this age, that means 48 and 142k, that means of age 48 and loan amount 142k. So there is high chance that he is going to default. Okay, so this is how the crude way of k nearest algorithm or KNN works. Okay, so now couple of points over here. So how to determine or how to take the value of k over here, one question, right? The second question, so question number 1 is, let us write it down over here. So question number 1 is, what is the optimal value of k? Optimal value of k. The second question is, okay, so now if you see, we have a lot of features like age, loan, right? And all of the features are defined in a different units, right? So my age is in years, and my loan amount is represented in dollar, right? So now, as the value of this dollar amounts are very high compared to these age values, it may happen that this feature have more impact, okay, right? More impact on the data, on the final outcome. So how to solve this one? Now if I just talk about the first one, right? So what is the optimal value of k over here? Now there are a couple of methods. I think one of the methods is, if you just redo this experiment again and again with lot of k values, different k values, okay, you may come up with this kind of graph. Okay, so if I just draw a small graph over here, okay, and in graph x-axis, if I just plot k value, and if I just y-axis, if I just plot the error or validation error, okay, that means whether the output is matching with this or not, okay, you may come up with this kind of graph, okay, okay, where if you see, when initially k equals to 1 and k is increasing, right? So at till this point, if I just point it out over here, till this point this error is getting decreased and decreased. That means this is the minimal point or optimal point, where till that point my validations error are less. After that point, if you see, the error is going up. So you will see this kind of behavior always when you experiment with lot of k values and draw this graph, right? So this is the k value you can choose. Okay, this is one way. There are lot of cross validation method of cross validation. When we'll be discussing about cross validation methods, we'll be discussing in detail like what are the different cross validation methods possible. Okay, so this is one way. Or generally in other way, by if your data points are less or how they are clustered, by seeing the data point itself, you may be able to determine what will be the optimal value of k. So generally, as I said before, if you take k's value between 3 and 10, you will be getting a good result out of this particular algorithm. Okay, so now question number 2 is, now how to solve this anomaly over here, right? Because there are a lot of features with different units over here, right? So for that we use the method called standardization. Okay, so if I just go a little bit down, standardization. Okay, so what is that? Now for each and every feature, the new value of the feature, that means if I just present it as xz, that will be the current value of the feature minus minimum value of the feature by Control-C, maximum value for that particular feature minus minimum value for that feature. So let us, if I just copy this guy over here again, okay, so what I'll do is I'll just go over here, copy it, and if I just paste this guy over here again, okay. Now for age, so if I just want to standardize age, that means for age, the new value of age will be x of age will be, what is the current value of age? That means for the first row it will be 25, right, minus what is the minimum value of age, that is 20 over here, right, minus 20. What is the maximum value of age? If I just go through it, it is 60, right, minus what is the minimum value of age? It is 20 again. So this will be the new value of age. I think this reduced to 5 over 40, that means 0.125, right, nearly. So similarly for loan also you can do the similar calculations, right. Now if you see, by using this formula for the fourth row where age is 20, right, so it will be becoming 0, but that is fine, because if you just apply it over here, so all the values will be between 0 to 1, right. So in that case no feature will have more influence on the output. Okay, so we can do something like this. Now if you see, whatever the distance formula we have discussed over here, these are mainly works for the variable of continuous type. That means this feature value take any value for a range, right. Now we can have a feature with discrete value, just let's say male and female, we can have a feature like that itself. Okay, so in that case generally we use hammer distance. Okay, so if I just give, it's actually Hamming distance, not hammer distance. Okay, so it is defined as summation I equals to 1 to n, if I say all our features in discrete in nature. So it is similar to our Manhattan distance, okay, but where if xi equals to yi, so suppose we have a feature set something like this. So if I just draw a small table, okay, suppose we have two features, okay, let's say x, y, okay, and we have some values, let's say male, female, male, male, okay, and the distance will be if both are same, that means if xy equals to yy, right, so distance will be 0, and if xi not equals to yi, the distance will be 1. So in that case distance will be 1, this case distance will be 0. So this is how we approach the features which are discrete in nature as well. Okay, so hopefully I have not confused you guys. So KNN is actually a very simplistic algorithm where the base point is like we just need to determine the distances of nearest point. Now how many point we'll be taking, that depends on our k values we are taking, right, and then those points are basically voting for that particular point. Based on that vote, whichever is winning, so that particular point class will be that particular class, right. So over here if you see that it is all our points are voting for red, so that's why the class for this guy is red over here, right. So now if I just just increase k infinitely, right? So in that case, what will happen? Our whole boundary will be this whole one. So if I just draw a fictional boundary here, okay, so I'll draw with this color. So if I just put k equals to infinite, so that means this our whole data set will be a single point, single circle, right? In that case, the value of this particular guy will be dependent on whether we have more number of blue points or more number of red points, but that doesn't make any sense over here, right? Now before we wrap this up, let me show you one interesting diagram over here. So here we are basically plotted or basically draw the border, right, when k equals to 1, 3, 5 and 7 for a certain data points. And if you see it over here, when k value is very less, right, that means it's 1 means the point itself. When it is 3, that means very basic 3 nearest point we are taking, right? That means this particular boundary will be very much overfitting the graph. When we are increasing k value, this particular boundary is getting smoother and smoother and smoother. Okay, so this is the effect of increasing the k. That's why if you see it over here, when we increase k to infinite, our boundary is the most smoothest one. That means the whole data set itself. So basically what we are doing it over here, when we are setting some k value, right, we are basically drawing a boundary between the two data sets. Basically in our data sets we are drawing a boundary which is basically segregating these data sets into two different classes, right? So that boundary, if that boundary is becoming something more and more touching all the data points, that means it is basically overfitting the graph. And when we are increasing the k value over here till infinite, it is basically smoother. That means it's basically underfitting. And that is actually, if I just show you over here. So when we draw this k value and the error graph, right? So initially when we increase that one, the boundary gets smoother and it becomes a minimum error point, right? After that, the boundary is getting more and more smoother, but it's increasing the error over here. That means we are basically underfitting over there. Okay, so hopefully this is intuitive enough. Okay, in next video we'll talk about another algorithm called naive Bayes. Okay, see you in next.